In this video, I want to make clear the distinction between flood frequency analysis and flow duration curves, which basically use the same kind of data, that is a sequence of discharges, in an attempt to make inferences about the likelihood of discharges of a certain size or larger. Let me remind you what a typical flow duration curve looks like. So here we have the probability, the exceedance probability, that is the probability that a discharge of any given size is exceeded. And the key point here is that we typically are interested in values that are common for the river. So we're interested in values that lie between, let's say these are our data points that are used to generate this flood duration curve. We're interested in values of discharge and values of probability that lie between the values we observe for our river. Typically, we might make observations for a year or two or even longer, and we have a pretty good idea of the limits, the lower limit and the upper limit of discharge. And what we really want to know is predict some exceedance probability for a discharge that lies between those limits. We're sort of interested in the middle ground here, the typical conditions of a river. Now, in flood frequency analysis, we're not doing that. What we're actually trying to do is figure out what's going on over here. That is, with the discharges that have a very low probability of being exceeded. In other words, discharges that are really large. These are floods. And so what we're interested in is not necessarily the data, in interpolating between the data we already have, but, and this is the real important point, we are interested in this region, and more often than not, we're interested in extrapolating our data to values of probability that are smaller than the probability that might be given with inferred from our data set using the expression P equals M over N plus 1. For example, if we might be thinking about annual peak discharges, and we might be thinking about the probability of a peak discharge that occurs on average once every 50 years, and we don't have 50 years worth of data. So we're never going to get a probability as low as 2%, which would be the probability equivalent of a 50-year return period in our data, but we need to infer what this value is. And so the point is that when we're doing flood frequency analysis, we are extrapolating our data to values of probability that are very low. This is typically how we perform the analysis. So what we're really interested in then is the actual shape of this curve. For a flow duration curve, it doesn't really matter. As long as we sort of have a curve we can use, it doesn't matter if it's straight or curved or what the form is, because we're interested in using it between these limits, right? Between the limits of our observational data. For the case of a flood frequency diagram, it really matters what the shape of this curve is, because we need to know how to extrapolate it beyond the limits of our data. And to do that, we're going to need to make some assumptions about what the statistical distribution is of the exceedance probabilities. And there are several different ways to approach that. The example I will give in this class uses a very simple model that works pretty well most of the time. Now, there's one other change that happens when we do flood frequency analysis, and that is because we're talking about probabilities that are really small, generally things on the order of 2% or that range here. Very commonly, instead of dealing with probabilities directly, we use instead the return period. So remember, the return period, RP here, or the recurrence interval or the exceedance interval, is just defined as the reciprocal of the probability. So again, there's no more or less information being conveyed when we use the return period. It's just that these numbers will be large instead of small, and very often it's easier for us to get a grip on large numbers than small numbers conceptually. So usually what we do is we recast this diagram in terms of the return period. And remember, in terms of return period, return period increases as we go from right to left on this diagram. So something with a low probability of exceedance has a high return period, or high exceedance exceedance interval, or a high recurrence interval, and something with a low probability has a relatively, I'm sorry, low probability has a high return period, high probability has a low return period. And so when we do that, our graph will actually look sort of like this, with the larger discharges having a larger return period. So that, remember, a larger return period means a smaller exceedance probability in any given year. So our graphs will have this form with a positive slope when we plot discharge versus return period, instead of the negative slope we always get when we plot exceedance probability versus discharge.